Good evening, all. Is my voice audible? Hello. And the slide is also visible, right? So today I have taken few questions from GATE 2014. So the first question is, which one of the following microstructures of a nickel-based superalloy imparts the highest grip resistance? So first let us know what is grip. This is basically time-dependent deformation. So normally, if we consider a material and we deform that at a low stress that is much below the yield stress of the material. So at normal temperature or at room temperature, nothing may happen at that stress level. But if we increase the temperature at high temperatures, we apply the same load that is below the yield strength of the material, much below the yield strength of the material, then deformation will occur. Why? This is because at high temperatures, the thermally activated processes such as diffusion becomes active. So this is the reason why at high temperatures, at much low stresses, we get plastic deformation. So there are different mechanisms. One is diffusion based processes, diffusion based mechanisms, and what comes under this category? Nabarro herring creep and cobble creep. So just remember, in Nabarro herring creep, what happens? The diffusion happens through the lattice, and in cobble creep, what happens? Diffusion through grain boundary. So we know that grain boundaries are so grain boundaries are basically obstacles for movement of dislocations. So suppose this is our consider any microstructure. If it has these are the grain boundaries, these red lines. So if there are much grain boundaries, so what happens? When a dislocation is passing through this in this direction, it will be stopped at this point because the orientation here is something, you can assume something like this, and in this grain the orientation changes. So it is difficult for the dislocation to pass through grain boundaries. That's why it imparts strength at low temperatures. So what happens at high temperatures? At high temperatures, we know the grain boundary areas are random as compared to the inside the grain areas where there is a systematic orientation. So there is randomness at the grain boundaries and there is much open space. So as we have much open space, diffusion becomes easier through grain boundaries. Okay. So then what happens? Grain boundary sliding occurs at high temperatures.
Sir, can
So
you repeat how we get much more open space?
okay, so I will draw one grain boundary here. In this region, we have something orientation like this. Suppose, okay, these are the crystal planes, and in this direction, we have something like, suppose, like this. Okay, so this is the region where the two grains meet. Okay, so as there is no continuity in the lattice, so this is why the grain boundary is random, but there is no ordered structure of the grain boundary. That's why. So imagine like this, something coming like this, one orientation, and in other orientation it is coming like this. So in this region, there will be much open structure as compared to this, much disorder. So that's why pipe diffusion you might have heard. So that's what happens along these grain boundaries. The atoms can move easily through the grain boundaries. Okay, so region is only basically we have much randomness in this region. So that's why there is no ordered structure. So there will be much open space as compared to inside of the grain.
Okay, sir.
Okay, so now we'll go to the question. So which one of the following microstructures of a nickel-based superalloy imparts highest grip resistance? So which one should be? Anyone can tell? Fine grain aqueous, coarse grain aqueous, columnar, single crystal. So just try to find out which has minimum grain boundary area. So these all have grain boundaries. Fine grain, coarse grain, columnar. This is the one single crystal, that means only one orientation. There is no grain boundaries. Okay, so this will be our answer. If this was not there in the option, then what would be the answer?
Course.
Coarse grain, yes. Okay, so clear. This one, this question is clear, right?
Yes, sir.
Okay, so this is one material balance question. So a direct reduced iron produced from a gas-based process contains Fe, FeO, C, and remainder being Gang. Chemical composition of DRI is total Fe is equal to 92 weight% and metallic Fe 84% weight%. Okay, so we have to find out the weight% of FeO in DRI. So suppose we assume total we have 100 kg, then it will be much easier to calculate. 100 kg of total hot metal. Okay, So what is the total Fe? 92%. So and the metallic Fe is 82%. So how much Fe is in FeO? 92 minus 84, 8 kg Fe is contained in
Yes.
FeO. Okay, 8 kg Fe is contained in FeO. So then how we calculate in this type of questions? Always write the equation Fe plus half O2 equal to FeO. So what is, if we consider the molar weight, we can take kg moles also. Let's take 56 kg. Fe is required to produce FeO. FeO, what is the molar weight? 72. Okay. To produce 72 kg FeO, we need 56 kg of Fe. So from 8 kg Fe, how much FeO we can produce? So can someone calculate this? 72 by 56 into 8.
10.285, sir.
10.2.
10.28 something. Okay. So this is our FeO that has resulted from 8 kg of Fe. So it has, what is the question asked? The weight percent of FeO in DRI. Okay, so as we have assumed 100 kg total, so this will be our answer, 10.28 kg FeO. So in this type of reactions, always you write the equation, then write the molar masses and balance that. Like for 72 FeO, we need 56 kg of Fe. Then from 8 kg Fe, how much FeO we can get? Very simple question. Is it clear? Or anyone could not understand? Tell me, please.
Understood, sir.
Okay. So this question is about the Pilling-Beddoes ratio. So what is it basically? Volume of oxide by volume of metal. But here you have to consider only the oxide that is produced from 1 mole of metal. So I will give one example. Suppose we have any metal M plus 3 by 2 O2 half M2O3. Or we can take directly an example of chromium Cr plus, okay, from 1 mole of chromium we produce half mole of Cr2O3. Okay, so this one you have to remember. Always you have to divide. So what will be the PV ratio of this?
2.
Okay, first you have to know the volume of this Cr2O3, whatever the volume is, half into volume of Cr2O3 divided by volume of M. So always you have to consider the oxide, the volume of oxide that is produced from 1 mole of metal. Okay, from 1 mole we have produced half mole of Cr2O3. So we have to multiply this half here always. You cannot just take the volume of Cr2O3 and divide by volume of Cr. That will be the correct answer. That will not be the correct answer. You always have to consider the coefficient here. Okay, so
Okay,
from
sir.
this Okay, so from these options, which one is correct? The molar weight of an oxide divided by the molar weight, not molar weight. This is not right. The volume of oxide divided by the volume of the metal consumed in oxide formation. Yes, this one. Note this part. The volume of the metal consumed in oxide formation. That means if we have consumed 1 mole of this, whatever moles we are producing, we have to multiply by that. So this one will be the right answer. Or if we are considering volume of Cr2O3, 1 mole, then we have to multiply 2 here. Okay. If you consider 1 mole of Cr2O3, you have to multiply 2 because 2 mole we have to use to get 1 mole of Cr2O3. If we get 2 here, we will get 1 mole of this. So always remember, so easy to understand is always take 1 mole of metal and whatever moles of the Cr2O3 or oxide is formed, always remember the coefficient and multiply that coefficient to volume of the oxide.
Okay, sir.
Two identical engineering components are made from alloys X and Y. The K1C of Y, okay, of X is greater than K1C of Y. So, if these components are subjected to the same stress, so the sigma applied is same in both cases during operation under mode 1 loading. So, mode 1 means suppose this is our material, we have a crack here. Mode 1 loading means always this crack opening mode. So, which one of the following statement is true? Component made from alloy X can tolerate a larger flow size compared to that made from Y. Component made from Y can tolerate larger flow stress to flow size compared to that made of X. Both can tolerate same flow size, none. So what should be the answer? We have the fracture toughness of X is greater than Y. So we know fracture toughness is some geometric constant. Suppose I take that A. So this is the geometric constant that comes from the origin of the crack. Like if it is surface crack, then this is 1.1. If it is center crack, something crack like this, so then this A is 1. So here you don't have to consider this, just forget it. So sigma pi a, this is the semi crack length, this is the applied stress. So this is same for both cases. So what should happen to the A? Which material can withstand more larger flow size, X or Y? This is same for both cases. This is also same. So if this is larger for X, then this A should be also larger. So material X can withstand larger flow size. Alloy X. So this one component made from alloy X can tolerate a larger flow size compared to that made from Y. This will be the right answer.
Sir,
Is it
please explain once again
okay?
from the formula part.
This one.
Yes, sir.
Okay, so I'll write it here again. So forget about this. This is a geometric factor. Depending on the if it is crack is surface crack, then this is something close to 1.1 for surface cracks, and 1 for this type of cracks, center cracks. Okay. So as you have considered the same crack geometry here, so forget this. So we have to consider these three only. Sigma applied is same for both cases as it is given in the question. So this pi is also constant. So that the question is asked that which material can withstand a larger flow size. That means this A. So we know that K1C of X is greater than K1C of Y. That means for X, the K1C value will be higher. So how? Because these two are constant already. So this A has to be higher for this K1C to be higher for X.
Yes, sir.
Okay, so that's it. The component made from alloy X can tolerate a larger flow size compared to that made from Y.
Okay, sir.
In this question, it has given two copper nickel alloys, one with 47 weight% nickel, other with 53 weight% nickel, are kept in separate crucibles and are allowed to equilibrate at the same temperature T1 between the liquidus and solidus line. So then what happens? First, let's draw the phase diagram. Copper nickel phase diagram, we know that is isomorphous phase diagram. This is for copper, this is nickel. Weight% nickel in this is 100% copper, this is 100% nickel. This is the melting point of Cu, melting point of Ni. So what has asked is we take one temperature T1. At this temperature, we consider two compositions. One is 47 weight% nickel, another one is 53 weight% nickel. Okay, so what will happen? The option A is same weight fraction of the liquid, but liquid compositions are different. So because here we know that from Lever rule, what will be the composition at this point, what will be the composition of liquid and what will be the composition of solid. This one, this red one, everything is red here. This is the liquidus line, and this one is the solidus line. Okay. So what will be the composition of liquid and what will be the composition of solid for this composition? So we have already drawn a tie line at T1. So for this composition, suppose we will take this as this one is A, this point is B, this point is C, this is D. So for this composition of this B point, the composition of liquid will be this A, and the composition of solid will be this D. Okay. Similarly, for this composition also, C, the composition of liquid will be A and D, because the tie line, wherever the tie line cuts the liquidus and solidus, that will be the composition of the liquid and solid for any particular composition. Is it clear, or I should explain again? Any composition you take, you first draw a tie line. Wherever the tie line cuts the liquidus and solidus line, that will be the composition of liquid and solid at that composition. So if I had taken a tie line at this point, so for this 47 composition, the composition of liquid will be this and the composition of solid will be this. If we take here a tie line, okay, for this composition, suppose 53 weight%, the composition of liquid will be this, composition of solid will be this. Is it clear?
Yes, sir.
So what has the question asked? I will draw the ABCD line here. This is our A, This is our B, C, D. This is our 47 weight percent. This is 53 weight percent. So how do we calculate the fraction of edges using lever rule? For this composition at B for 47 weight percent, what will be the fraction of liquid? How to calculate? So remember, if you have to calculate the fraction of liquid, so this one is our liquidous line, right? So you have to take this BC, not BC, BD, this whole length, okay, fraction of liquid for 47 weight percent nickel. This will be BD divided by AD. Okay, so this length BD divided by this whole length AD. So this is the lever rule. And what will be the fraction of solid? For the same 47 weight percent alloy, that will be, when you have to take the fraction of solid, you have to go this side. This AB divided by this whole length AD. Okay, if you have to calculate fraction of liquid, you take the opposite direction. If you have to take the calculate the fraction of solid, then you go in the opposite direction. So for liquid, we calculated this BD divided by AD. For solid, we calculated this AB divided by AD. So is this lever rule clear? So if it is clear, then you can tell me what will, for this 53% weight composition, 53% nickel, what will be the fraction of liquid and what will be the fraction of solid for this T1? Tell me in terms of A, B, C, D, like AB by CD or AC by CD, something like I have written here.
So liquid CD upon AD and
Hmm.
solid AC upon AD.
Yes. So what did we see? The composition of liquid and solid fractions will be same for both the compositions. This will be this and this for both the compositions. Composition is same. So only what will vary? The weight fractions of the two phases, liquid and solid phases, will vary. So then we will check the options here. The same weight fraction of liquid and solid. Liquid, but the solid composition, then this is not correct. Same composition of liquid, but the weight fraction of liquid are different. This is fine. Same weight fraction of liquid, this is not correct. Different compositions and weight percent. Composition is not different, same composition. So this one is the right answer, B. Same composition of the liquid, but the weight fraction of liquids are different. So on this lever rule, every year one or two questions compulsory. So understand it properly. This is isomorphous diagram. They might give eutectic diagram or peritectic diagram, some complicated diagram, but the principle is same. You just have to draw a tie line, and then you have to calculate the phase fractions.
Okay, sir.
This one is a pretty easy question. I think some of you might know this. So anyone can tell me the answer? These type of questions you should be able to solve within 5 to 10 seconds. This is a 2 marks question, but it won't take 10-15 seconds maximum, not more than that.
Sir B.
How?
So the product of a dislocation on the plane is zero. So one bar one zero is dislocation and one is plane. When we got the product, it will be zero.
No, no. First, read the question properly. On which plane do these two partial dislocations lie? So you have to consider the right side two partials, not the left side one, a by 2, 1 by 0. On which plane the partials lie? That means the two partials, those two you should consider for dot product. And test with the each of the options. Which one gives 0 for both of the cases? That will be the answer.
So D, option D.
Hmm. That is the right one. So that's basically we know that this is one plane and a direction lies in this plane. Suppose this is our slip plane and this is the slip direction. Okay. So as the direction is lying in the slip plane, the normal to this plane, that is going out of this plane, out of this surface at this point. So that will be normal to this direction. So the dot product of the two must be 0. So here we take 2 1 bar 1 dot 1 1 1 bar. So 2 minus 1 minus 1, this will be 0. Similarly for this case, 1 2 bar 1 bar dot 1 1 1 bar. This is 1 minus 2 plus 1. So this is also 0. This is the right answer. Within 5 seconds, you should be able to do this type of questions. So a body starts yielding when it is subjected to a stress state with principal stresses of 250 MPa, 50 MPa and minus 50 MPa. So what is the yield strength of the material in MPa if Tresca yield criterion is obeyed? So how to solve this? So first let us have some idea about what is Tresca yield criteria is. So this is if principal stresses are given and sigma max minus sigma min by 2, that is our maximum shear stress. Okay, so this we also can see if we draw a Mohr circle. Okay, in this direction I have taken the sigma xx, in this direction tau xy. Suppose we take a 2D stress tension. Okay, so how to draw a Mohr circle? So first you take sigma xx value, this one, and tau xy. You look at one point sigma xx and you look at tau xy, one in this direction, downward direction, one upward direction. So for this sigma xx, suppose this is the point where you get this point is sigma xx, tau xy, and here sigma yy. And suppose this point is our sigma yy, tau xy. So how to draw a more circle? First, you connect these two lines, these 2 points. Wherever it cuts, then you draw a circle. The radius is this. Okay, so wherever the circle cuts this x-axis or sigma axis, this is your sigma 1 or sigma max. First principal stress, because here the tau xy is 0. Okay, wherever tau xy is 0, that is your principal stress. This is sigma 1 and this one is sigma 2 or sigma minimum. And this radius, this is your, the value of this radius is your tau max, maximum shear stress. So from here you can already see this relation, sigma max minus sigma minimum, sigma max minus sigma minimum divided by 2. That means this radius. Okay, this is your tau max. So everyone got this? Or anyone found it difficult? Should I explain this again?
Yes, sir.
Okay, so first you consider the stress matrix and the other components, sigma xx, sigma yy, and tau xy. This is the stress in x direction, this is the stress in y direction, and these two are the shear stresses. Something like this. If we draw the stress element, this is your sigma xx, sigma yy, and these two are tau xy, these two are also tau xy. Okay, so first how we draw this more circle? First we take this sigma xx value and this tau xy value. So one we take in up direction in this direction and one in down direction. Okay, for this, suppose this is our sigma xx value. Okay, so from sigma xx we go in downward direction for tau xy. What is the value of tau xy? Whatever this is, then I look at this point. Similarly, this is our sigma yy value, and we look at this point which is sigma yy and tau xy. We look at this point and we draw a straight line. Then we take this half length as the radius and draw this whole circle. So this is a more circle. Wherever this circle cuts the x-axis, that is our principal stress. This one here this one here. So in the question it is already given when it is subjected to a stress test with principal stresses of 250, 50 and minus 50 MPa. Okay, so I have drawn here a 2D Moore circle. Here it is given 3D. So for 3D we have to consider again three circles. Like we will draw that. Next slide. Suppose if it is given to draw 3D Moore circle. So first we have to draw a small one. I will explain this. First let me draw. This matrix we have to consider for 3D Moore circle. So first you take sigma xx, tau xy, you draw one circle. Then you take sigma yy, sigma zz, tau yz, you draw another circle. Then you measure this line, take the half of it, and then draw this whole circle, this big circle. Okay, so this one is our final Moore circle. So as per the question, 250 MPa principal stresses, one is 250, one is 50, and one is minus 50. So this one is our 250. This one is 50. This one is minus 50. Okay, so any fact the circle cuts the x-axis, those are the principal stresses because there the shear stresses are zero. So actually for this question you don't have to draw more circle. I just wanted to let you know this. So better you remember this 2D Moore circle. This is more useful and most of questions they ask from 2D Moore circle. If you know this, then you can directly get the answer without using much formula. Like what will be this length, what will be the maximum shear stress, everything you can get easily if you can draw the Moore circle directly.
Okay, sir.
So from Tresca criteria, we know that sigma max minus sigma min by 2 is equal to tau max, which I have shown here. Already from this figure you can see sigma max minus sigma minimum. Okay, so this is our sigma max, this is our sigma minimum. Are you seeing here? Sigma max, sigma minimum. So this divided by 2, this is our maximum shear stress. And also this value, so that means this is your yield stress. Okay, so if you are loading a material in two directions or in three directions, so always sigma maximum, this principal stresses, this is sigma max. The difference between the sigma maximum and the sigma minimum, that is always the yield stress of the material. Remember this. So here in this case 250, maximum is 250. sigma minimum equal to minus 50 MPa. So what will be the yield stress? 250 minus minus 50, 300 MPa. Okay, so this is your answer. So what if it asks to calculate the maximum shear stress? Just divide it by 2, 150 MPa. Okay, so is this clear?
Yes, sir.
So
Clear, sir.
also I can explain why we are taking this sigma yield strength equal to 2 times tau max. Okay, suppose we consider a state of pure shear. So in this case, what will be the Mohr circle? That will be around the origin. So if we draw the stress element, there will be only shear stresses and no normal stress. Okay, so as we can see here, at this point, the normal stress is 0 and only we have shear stress in this point also. So what is the condition for that? This is our sigma 1, this is our sigma 2, or sigma max, sigma minimum. These are the two principal stresses, sigma 1 and sigma 2. So the condition for pure shear is sigma 1 equal to minus sigma 3. As we can see here, this is our origin 0. So sigma 1 equal to minus sigma 2 or 3, whatever you can write. And sigma 2 is equal to 0. So why? Because this example we have considered two circles, like 3D Mohr circle. So that way you can say sigma 1, this one will be sigma 2. So sigma 2 is 0 and sigma 3 this one. Then what will happen to tau max? We know sigma max minus sigma min by 2. Okay. So what is your sigma max? That is sigma 1, this one, and sigma minimum is also sigma 3, which is equal to minus sigma 1 by 2. Okay. So suppose we assume this sigma 1 that is equal to the K. What is K? That is the yield stress in pure shear. So this is our basic equation for Tresca criteria. This is the yield stress. So let's take it as equation 1. So we put sigma 1 in this equation, sigma 1 equal to k. In this above equation, in 1, then what will happen? Sigma 1 minus sigma 3 equal to sigma 0, or this is yield stress sigma ys. So from this we get this relation that sigma 0 is equal to 2k. So what is 2k? This k, this is basically our tau max. So that's why I use this equation by 2. When this 2 goes to this side, this becomes our yield stress, this one. So you can directly write sigma max minus sigma min equal to sigma ys. This is 1 for Tresca. Also you can write sigma max minus sigma min by 2 equal to tau max. These are the two forms of Tresca criteria. Okay, so just remember these two. So any question in Tresca criteria you can solve using these two only. If it is as per yield strength, just take sigma max minus sigma min. If it asks for maximum shear stress, just divide it by 2. That's all. So anyone want to ask anything, or we should end this session?
No,
Sir,
sir.
Okay, so thank you for joining. See you all in next week.
sir, what will be the next topic, sir? The next class.
Next class, actually I haven't updated that in the portal. I will update it, and then you can check that in the portal itself.
Okay,
So
sir.
because we already have so much work, then actually they are assigning few gate questions that we have to solve. Make videos of 5-6 minutes and upload that in gate portal NPTEL. So I'm taking those questions here, but I think it would be better if I take only one concept and teach that and take few questions regarding that concept only. So that will be, I think, more beneficial for you people.
Yes, sir. Yes,
Yes,
sir. This is more beneficial.
Okay, so next time, uh, what do you want? Which subject?
thermodynamics, sir.
The,
Thermodynamics is huge. I mean, I have to take only for one in 1 hour.
Solutions.
Solution
oh, sir.
thermodynamics.
Yes, sir.
Okay. Okay, so next week we will discuss solution thermodynamics.
Thank you, sir.
Welcome.